This is video lecture for section 7.2 for business calculus on substitution, also known as U-substitution. So integration by substitution is basically the chain rule for derivatives in reverse. Remember, when we're finding antiderivatives, we're undoing or reversing the differentiation process. And so remember, the chain rule tells us when we take the derivative of a composition of functions, so you have f composed with g of x. When you find the derivative, first you take the derivative of the outermost function, you leave the inside function alone, and then you multiply by the derivative of the function that's on the inside. So this is the derivative of f composed with g of x. Now that we're finding antiderivatives and we're integrating, we want to go backwards. So the integral or antiderivative of f prime of g of x times g prime of x dx is f composed with g of x. But when you're just staring at the problem and it's given to you like this, it's really hard in your head to be like, oh, I know what f composed with g of x would be that would give me this as a derivative. It's hard to just stare at that. So what we do is we make a substitution to kind of help us break down the process and see what the original function was to find the antiderivative. So here's how it works. We substitute u for g of x. So this inside function we replace with u. Then the next part of the process is you want to rewrite this whole integral in terms of u. So you don't want to have any more x's in there since the new variable is going to be u from the substitution. How do we do that? Well, once you've already chosen, you say let u be some g of x. Then you find the derivative, u prime, which is the same as du dx, would be g prime of x, which is what is right here. Du dx is g prime of x. Then you break off that differential dx. Remember, we can split these guys up sometimes. And then I can write this as du equals g prime of x dx. That's exactly what's right here. And so all of this here, g prime of x dx, that's your du. So your integral becomes integral, you would have f prime of u du. And then it's a lot easier on your brain. This is f prime of u, and you go, oh, I can find the antiderivative. I got this, okay? It takes a little while to get the hang of it, but once you see the pattern, you'll be able to do this pretty seamlessly. Just don't get frustrated with yourself. It's normal. It's tricky in the beginning, okay? Don't cry. Here we go. Find antiderivative of 4x plus 3 over 2x squared plus 3x minus 2 cubed dx. So in the beginning, you might guess wrong who to let u equal, and that's totally normal, okay? If I were you, I would leave my wrong guesses on my paper, on my work, and just put a big X through them because it's helpful when you look back to see why those choices didn't work out for you. Now, here's something to keep in mind. Whatever you pick u to be, its derivative has to appear in the integral. So what do I mean by that? Usually, you pick u, it's going to be the inside function in a composition plus its derivative needs to be hanging out multiplied in the integral somewhere. So here's how I'm looking at this. We've got all this stuff raised to the third. That looks like a composition of functions to me. We've got an inside function and then all this stuff is being raised to the third in the denominator. So I'm inclined to let all of this be u. That whole mess, I know. So I'm thinking we're going to let u be 2x squared plus 3x minus 2. Now, for me to know if that's a good choice, I'm going to have to take the derivative in the next step, and I better see that derivative in the integral, which I will. Someone sat there and wrote this to be a beautiful problem for us. Okay, so the derivative with respect to x, du dx, would be 4x plus 3. Do you see that? Yes, I do. Here it is. And remember, you want to rewrite this whole integral in terms of u. You don't want any x's. And so we got to split this little dx, move it over here. And then I write du equals 4x plus 3 dx. And then that's exactly what I see here. Oh, beautiful. I always tell my students, draw the little kidney bean. This kidney bean here, who is it? It's du. Wow, okay. So instead of that kidney bean, I've got a du. It's in the numerator. You'll never have du or dx in the denominator of your integral. It has to be in the numerator or just off to the side, not in the bottom. Over, well, remember, instead of 2x squared plus 3x minus 2, I'm replacing that with u to the third. That exponent stays. How are we doing? I haven't taken an antiderivative yet. I'm just making a substitution. I'm changing all the variables. But now, look, what an extreme makeover. This messy thing became, boom, integral du over u cubed. Now, I would recommend right now, just rewrite that. That's the same as integral u to the negative third du. Yes? Good. And then now we can take the antiderivative. So add 1 to the exponent. Negative 3 plus 1 is negative 2. Be careful. And then divide by the new exponent. And then don't forget to put plus c. Ooh, so many dangerous maneuvers. Okay, so this is negative 1/2 u to the negative second plus c. So I'll write that as negative 1/2. What was u? It was 2x squared plus 3x minus 2 to the negative second plus c. So once you find the antiderivative, nobody wants it with u's in it. You have to give back the answer using the original variable of the integral. So I'm replacing u now with what it originally was, 2x squared plus 3x minus 2. And then I wouldn't leave it like that. I would rewrite that negative exponent in the denominator, and that 2 is going to go down there with it. So I'd write it as negative 1 over 2 times 2x squared plus 3x minus 2 squared plus c. Okay, how was that? You probably didn't like it because it's new and it might feel tricky, but don't worry. You'll get the hang of it. I promise. I promise. Here we go. Let's try another. When you're trying to find u, let u be the inside function in the composition. Do you see a function inside another one? Like, look, 5r squared plus 2 is underneath the square root sign. That's a good choice for u. Okay, so let's let u equal 5r squared plus 2. Now, you'd have du dr equals 10r. Move the dr over, so du is 10r dr, and then I go, I better see this in the integral somewhere. Do you see it? Kind of. I just have r dr, so let me draw my kidney bean, r dr. I can get r dr by itself if I divide by 10. So 1/10 du is r dr. So I can replace the kidney bean with 1/10 du. And then all I would be left with is square root. Instead of 5r squared plus 2, that's going to be u. Okay, so let's see. New integral, square root of u times 1/10 du. Now, let's make sure everything makes sense. Square root, that was u. Boom. Kidney bean, 1/10 du. All right. Now to find the antiderivative, I would recommend taking your constants outside the integral sign just so it looks less messy. It'll help your brain focus, okay? So this is going to be 1/10 integral. Instead of square root of u, think of it as u to the 1/2 du. Okay. Add 1 to the exponent, divide by the new exponent, and this 1/10 just comes along for the ride. So we've got 1/10. Adding 1 to the exponent is going to be u to the 3/2. And you guys, let's do a trick now, little shortcut moment. Dividing by the new exponent, dividing by 3/2 is the same as multiplying by the reciprocal 2/3. Yes? Yeah, just cut to the chase. Go straight there. And then plus c. And then from here, this will simplify. 2 and 10 cancels. That's 5. This is 1/15 u to the 3/2 plus c. Should I box this? Are we done? No, no, no. You got to give back the original variable of the problem. Yeah. So remember, u is 5r squared plus 2. So replace that u with 5r squared plus 2. So your final answer should be 1/15 times 5r squared plus 2 to the 3/2 plus c. Boom. How was that one? You got to just do lots to get the hang of it and to start recognizing patterns for how to choose U. And how many is lots? It depends on the person. It depends on the student. So everybody takes a different amount to finally have this click. Okay, but you can get there. Let's keep practicing. We have integral x squared minus 1 times e raised to the x cubed minus 3x dx. So just take a guess what you think u should be. Write it down and then take its derivative. If you don't see the derivative in the integral somewhere being multiplied, then that was the wrong choice. So like, let me give you an example of a bad choice, okay? Maybe you're like x squared minus 1. Let u equal x squared minus 1. Then du dx would be 2x. And then we move the dx over. So du is 2x dx. Do you see that anywhere? 2x dx? No. So I go, abort mission. That was not the right choice. Okay. Maybe you think I should let it be e raised to the x cubed minus 3x. So if u is e to the x cubed minus 3x, then du dx, what's the derivative of e to the something? It's e to the something times the derivative of the something. So then I'd need to multiply by 3x squared minus 3. So if this is u, I need this to show up somewhere else in the integral. No, I don't have that either. So that was no good. Abort mission again. So what to do? Oh, what was that? What choice have I not made? Letting u be just the exponent, not with e. Okay, so let's try that. This time, let's let u be just x cubed minus 3x. Then du is 3x squared minus 3 dx. You might be like, whoa, Professor V, you did something wild right now. I know. Instead of writing du dx, I already moved the dx over. Feel free to do the same, because when you do u sub, that's always the next step. So just hop to it. Do you see 3x squared minus 3 over here? Kind of, not exactly, but I can get there. Where unlike the last two scenarios, I couldn't get there. If I take a 3 out, factor it out, then I have x squared minus 1. So du would be 3 x squared minus 1 dx. And then, yeah, I'm almost at, here's the kidney bean, x squared minus 1 dx. 1/3 du is x squared minus 1 dx. Yay! Okay, so it's totally normal. Don't be embarrassed if you have to go through this part of the process. I've just done thousands of integrals at this point that, usually I can see it right away. You'll get there. So now let's carry on with the substitution. The kidney bean, all of this is what? It's 1/3 du. I'm going to put the 1/3 outside, integral du. And then now I just have e, I still have e raised to the u. Yes? U is x cubed minus 3x. So I have e to the u. And then x squared minus 1 dx is 1/3 du. X squared minus 1 dx is 1/3 du. Can you find the antiderivative of this? Oh yeah, no big deal. Antiderivative of e to the u is e to the u. The 1/3 comes along for the ride, and just don't forget to put plus c. And then don't box it just yet. Got to go back to the original variable. So this is going to be 1/3 e raised to the x cubed minus 3x plus c. Love it. Excellent. Okay, so a lot of the times if you have like e raised to some function, let just the exponent part be u, okay? See if you can do this one on your own. Using the hint I just gave. It's very similar to the one we just did. Did you try it on your own? I'm going to let u be just the exponent, okay? Let u be square root of y, which is y to the 1/2. Then I'm not going to write du dy. I'm just going to write du equals 1/2 y to the negative 1/2 dy. I already multiplied it over, okay? But 1/2 y to the negative 1/2 dy is the same as 1 over 2 square root of y dy. Don't we have that? It's a very small little kidney bean. Here it is. Here it is. That's just du. All of that is du. And then this is e to the u. Oh my goodness. This is just so clean now. So this is integral e to the u du. Antiderivative is going to be e to the u plus c. Should we box it? No. Remember, u is square root of y. And I'm going to write it with the radical because that's how the problem originally was, instead of to the 1/2. You know what I mean? If they start with radicals, I usually give back the answer with the radical. If they had written it y to the 1/2, I would have ended like that. Okay, let's keep going. Hopefully you're having a little more fun now. Integral y squared plus y over 2y cubed plus 3y squared plus 1 to the 2/3 dy. This is very similar to the first one we did. So remember, let u be the inside function in a composition. I don't see a composition here. There is a composition in the denominator. I've got a function raised to the 2/3. So I'm inclined to let u be all of this stuff down here. Let's just try. Sometimes you take guesses and they're wrong. Other times you take guesses and they're right. So let's let u be 2y cubed plus 3y squared plus 1. Okay, then du, take the derivative, would be 6y squared plus 6y dy. I'm looking. Is this the rest of my integral? dy, y squared plus y, 6y squared plus 6y. I can get there, no big deal if I take the 6 out. Okay, getting excited. I think we chose correctly. So 6 times y squared plus y dy. Yes, now I've got my kidney bean if I divide by that 6. So 1/6 du is y squared plus y dy. So this whole kidney bean is going to get replaced with 1/6 du. Okay? Here we go. So now we have integral. The 1/6, I'm going to put it outside. Du is going to go up top. That looks ugly. Hold on. Over, and then all of this stuff is just u to the 2/3. How are you doing? I mean, look, this looks so nice and simple compared to what we started with. What a hot mess that was. Okay, so then this is 1/6 integral u to the negative 2/3 du. Now we can take the antiderivative, so don't write the integral sign, don't write du. You're going to add 1 to the exponent and divide by the new exponent. The new exponent is going to be u to the 1/3. And dividing by 1/3 is the same as multiplying by 3. And then put plus c. And then 1/6 times 3, that's 1/2. And then don't leave this as u. We got to go back to the original variable. So 2y cubed plus 3y squared plus 1 to the 1/3 plus c. And we are done. Nice, huh? Okay. I have just a few more. And then, of course, we're going to do a little econ application. Here we have integral of 4r times the square root of 8 minus r dr. So this is a famous kind of problem where you have the sum or difference, right, of a couple terms underneath the radical, and outside is just one term. And really what we want to do is switch it so that underneath the radical is just one term and outside we have multiple. That way we can just rewrite everything using our laws of exponents and take the antiderivative. You might be like, I don't know what you're talking about. I get it. Until you see it, it's kind of hard to see what the process is going to be or why it's helpful. But what we do is, again, let the inside function in the composition be u. So in this case, I'm going to let u be 8 minus r. Okay, the derivative, du, derivative of 8 is 0. Derivative of negative r would be negative 1 dr. So du is negative dr. Was this a good choice? Where you're like, okay, there's dr. So dr is negative du. But Professor V, we have a problem. U is 8 minus r. What am I going to do with this extra r out here? It didn't pop up here. I know. So what we do is we come back here to this u sub statement. Let u equal 8 minus r. Can you find or solve for r in terms of u? Because remember, my goal is I want to rewrite this whole integral in terms of u. So I don't want to have any r's mixed in there. Yeah, I can do that. If I move r to the other side, r plus u equals 8. So r is 8 minus u. So you're actually going to replace this r with 8 minus u. Okay, so watch. So now we have integral 4. Instead of r, I'm going to write 8 minus u. Then square root, not 8 minus r, but square root of u. And then lastly, dr. dr is negative du. But it's being multiplied. So that looks super weird. Take that negative, take the 4 outside. Take them outside. So negative 4 integral 8 minus u. Instead of square root of u, I'm going to write it as u to the 1/2 du. So why is that better? Because now underneath the square root, I just had one term, u. And if I write it to the 1/2, I can distribute it through to the 8 minus u, and then boom, find the antiderivative. You would have a much harder time trying to do that here because you don't have just one term underneath the radical. So by doing the u sub this way, we switched it. See, there was only one term outside, now there's two. There were two terms under, now there's one. They basically swap places. Okay, let's get this show on the road then. Negative 4 integral 8u to the 1/2 minus u times u to the 1/2 is u to the 3/2 du. And then now we're going to add 1 to the exponent, divide by the new exponent. So this is negative 4 times 8u to the 3/2 divided by 3/2 minus u to the 5/2 divided by 5/2 plus c. So what is this? Negative 4 times 8 divided by 3/2 is 8 times 2/3, so that's 16/3 u to the 3/2 minus, this will be 2/5 u to the 5/2 plus c. Shall we distribute the negative 4? Why not? So negative 64 over 3 u to the 3/2 plus 8 over 5 u to the 5/2 plus c. And then go back to the original variable. So don't leave your answer in terms of u. Who was u? I forgot. It was 8 minus r. So all these u's I'm going to replace with 8 minus r. And then while we're at it, like, don't you always want to put your best foot forward? I'm going to put the positive term in the front. Don't start things off negatively. That's more like a personal aesthetic preference, but let's do it. So 8/5, 8 minus r to the 5/2 minus 64 over 3, 8 minus r to the 3/2 plus c. Okay, and you might say, Professor V, I would have never thought to do that little maneuver earlier, right, where you had to solve for r in terms of u in order to substitute right here. And you know what? I didn't either. I didn't think of it the first time myself. I had to be shown this trick, you know, and that's okay. Sometimes you have to be given a hint and then you practice until you can recognize when to use it on your own. That's totally fine. Don't be embarrassed. Okay, I literally have only 2 more and then an application. So you guys are doing great. Hang in there. I would say try to do these next 2 on your own before you watch me solve, okay? Because it's all fine and dandy when you watch me go through, but when you're by yourself, it's a whole nother story. This is similar to the one we just did, but if anything, easier actually. So please try it. Remember, u has to be the inside function in the composition. So I'm just going to go for, let's let u equal x plus 5. Then du is dx, right? So that's taken care of. Dx I can replace with du. This is all u. And then what do I do with this extra 2x in the top? The 2 is cool. The x, I can't leave x's and u's in the same integral. I have to solve for x in terms of u, and you're going to do that coming right here. Right here. Can you get x by itself? Yeah, x equals u minus 5. So then now we're in business. This x, we're going to replace with u minus 5. Okay, here's our new integral. 2 times u minus 5 over, instead of x plus 5, you're just going to have u to the 6th. Instead of dx, that's du. Ooh, that was nice, right? Okay. From here, I would take the 2 out. And then you have u minus 5 over u to the 6th. So let's split the denominator, u over u to the 6th minus 5 over u to the 6th du. And then simplify so we can anti-differentiate. So u over u to the 6th, that's u to the negative 5th minus 5u to the negative 6th du. Good? Okay, the 2 stays out there. Now let's find the antiderivative. Add 1 to the exponent, divide by the new exponent. Be careful with negative numbers, right? So adding 1, the new exponent would be negative 4. And then that's dividing by negative 4 is the same as multiplying by negative 1/4. And then add 1 to this exponent. It's going to be negative 5. And then take negative 5, divide by negative 5, the new exponent. It's just going to be positive 1 plus c. How was that? Good, good, good. Okay, we can distribute the 2 back through. So that would be negative 2 over 4, or negative 1/2 u to the negative 4th plus 2u to the negative 5th plus c. And then go back to the original variable. So negative 1/2 x plus 5 to the negative 4th plus 2x plus 5 to the negative 5th plus c. I would put the positive one first, and then maybe let's just put the negative exponents in the denominator. So 2 over x plus 5 to the 5th minus 1 over, this is 2x plus 5 to the 4th, all in the denominator. Don't forget the plus c. Okay, whew. Last one, you guys. You're doing so well. Here we go. Integral of the square root of x squared minus 6x times x minus 3 dx. Any guesses what u should be? It's always the inside part of the composition. Did you say x squared minus 6x? Not with the square root. Just the inside stuff. So let's let u equal x squared minus 6x. Du would be 2x minus 6 dx. Do I have that? If I factor out a 2, I do. So du is equal to 2 times x minus 3 dx. Here it is. Here it is. So divide by that 2 now. So 1/2 du is x minus 3 dx. So all of this gets replaced with 1/2 du. And then the rest of my integral is just square root of u. Square root of u. So I can rewrite it now. When you get slick, you just go 1/2 integral square root of u du. Yeah? Good. And then rewrite that. That's integral u to the 1/2 du. Add 1 to the exponent, divide by the new exponent. So you're going to have u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. And then plus c. Don't forget the plus c. Simplify, the 2's cancel. And then this is 1/3 u to the 3/2 plus c. Should we box it? Only if you want minus 1. I don't think you have points to waste. 1/3. Who was u originally? Right here, right here. X squared minus 6x. So x squared minus 6x to the 3/2 plus c. Fabulous, you guys. Well done. Okay, here we go. Little application problem. A company incurs debt at a rate of d prime of t, which equals 90 times t plus 6 times the square root of t squared plus 12t dollars per year. T is the amount of time in years since the company began. So remember, derivatives give us instantaneous rate of change. This is the rate at which they're accumulating debt. By the fourth year, the company had accumulated $16,260 in debt. So what this is doing is giving me an initial condition so I can solve for C eventually. But basically this means the debt after 4 years, when T is 4, is $16,260. So now they're asking us first to find the total debt function. They want us to find capital D of T, not D prime, not the rate at which the debt is accumulating, but just the debt function. So how would we do that? They gave me the derivative. I need to take an antiderivative. I need the integral of D prime of T dt. Okay, so this is going to be the integral of 90 times T plus 6 times the square root T squared plus 12T. Don't forget, very good, dt. Now, no surprise, in order to do this antiderivative, we're going to need to make a substitution. This is so similar to the one that we just did. So we're going to go ahead, let's let U equal the stuff underneath the radical sign. So just t squared plus 12t. And then du is 2t plus 12 dt. How are we doing? Do I see that? No, I just see t plus 6, but I can get there if I factor out that 2. So du is 2 times t plus 6 dt. So 1/2 du is t plus 6 dt. So let's see. T plus 6 dt is 1/2 du. And then what about the 90, you're probably thinking, because this is going to be rad u. This is 1/2 du. 90 just comes along for the ride. In fact, put it outside if you want. 90, you're getting exiled. Okay? Yeah. And then we're going to have integral. T plus 6 dt is 1/2 du. Let me put the 1/2 out there with the 90 so it's not so lonely. Du. And then we have square root. All of this is just u. Good? Okay, we're ready to roll. This is 90 times 1/2, that's 45. Square root of u is u to the 1/2. So the antiderivative is going to be 2/3 u to the 3/2 plus c. And then cleaning up, this tells me then d of t is 45 times 2/3. That's going to be 90 divided by 3, or 30. Instead of u, I'm going to write what I originally had, the original variable, t squared plus 12t. T squared plus 12t to the 3/2 plus c. This is what I have so far. But then remember they told me d of 4 is 16,260. That's so I could go ahead and find c. So let's do that over here. So d of 4 equals 30 times 4 squared plus 12 times 4 to the 3/2 plus c. And this all equals 16,260. This is 30 times 16 plus 48 to the 3/2 plus c is 16,260. This is 30 times 16 plus 48 is going to be 64 to the 3/2 plus c is 16,260. This is going to be square root of 64, which is 8 cubed, times 30, and then subtract it over to the other side. Cutting to the chase, c is 900. So then now you can come in and say, all right, I know c is 900. So I'm going to replace this c right here in my total debt function accordingly, and then just write out d of t is 30 times t squared plus 12t to the 3/2 plus 900. Okay, good. Not too bad, right? Now, part B says how many years must pass before the total debt exceeds 40,000. So now that we have the debt function, I want to know how long it takes for this to be more than 40K. So I'm going to set it equal to 40,000 and solve for years, solve for t. Okay, so let's set d of t equal to 40,000. So that's 30 times t squared plus 12t to the 3/2 plus 900 equals 40,000. And this isn't going to take any calculus. It's just ugly algebra. My apologies. So first you would subtract 900, right? Okay, hang in there. 30 times t squared plus 12t to the 3/2 would equal 40,000 minus 900 would be 39,100. Then divide by 30, exactly. Divide by 30, divide by 30. And 39,100 divided by 30 is not an integer. It's 3,910 divided by 3. So we're just going to, since we're trying to solve for t, I'm just going to round that off, okay? It's about 1,303.3 repeating. So I'll just keep 2 decimal places. Check with your instructor how far they want you to take things, okay? But there's kind of no nice way around this, unfortunately. Now to solve for t, kind of strip away one layer at a time what's going on. I want to get rid of this 3/2 exponent. How do I do that? You raise both sides to the reciprocal of the exponent. Because remember, when you multiply these guys by each other, they'll cancel out and just give you 1. And then, whoop, you just got plain old t squared plus 12t. And then for sure, yes, please bust out your calculator and take 1,303.33 raised to the 2/3. If you want to preserve accuracy as much as possible, I would enter the fraction to the 2/3, not the one where you rounded it, okay? Just to be super, super careful. And you should get about 119.317. Okay, now look at this thing. It's disgusting, I'm sorry. It's quadratic. And so I'm going to set it equal to 0, and we're going to do the quadratic formula. T squared plus 12t minus 119.317 equals 0. Because it's not going to factor. There's no way around it. So A is 1, B is 12. That part's fine. And then C is, holy smokes, negative 119.317. I know. The good thing is, it's just, you got your calculator, okay? So you just punch it all in. Just set it up and then go for it. So T equals opposite of B plus or minus square root B squared minus 4AC all divided by 2A. You know, in 7th grade when I learned the quadratic formula, my algebra teacher made us make one-on-one appointments with her and come into class and recite it. And then we'd get like checked off. Anyways, let your calculator do the dirty work and figure all that out. You should get 6.465 if you're rounding to 3 decimal places, and then negative 18.464. So these represent time in years. As of now, we can't go back in time, so the negative 18 one does not work. And it takes about 6.4 years to hit exactly $40,000 worth of debt incurred. And they want to know how many years have to pass before it exceeds 40,000. So just round that up, say 7 years, right? Until we exceed 40,000. Oh, that's a lot of debt. Okay, so 7 years. Good? Okay, sorry the numbers were nasty, but you know what? It happens sometimes. And I would hate it when my teachers would always do easy examples with nice numbers, and then on my homework or the test, I had gross numbers. I thought that was very unfair. So here I am, I'm doing the gross numbers with you. Okay, guys? That concludes the lesson. Don't forget to give the video a thumbs up, subscribe if you haven't already. I think we only have like 2 more lessons to go, so stay tuned, make sure your notifications are on. You can follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later.